Imagine a universe far more complex than anything we've ever known, where reality extends beyond our observable 3 dimensions of space and 1 of time. What if there were not just 11 but 13 dimensions shaping the fabric of existence? Today, we'll embark on an extraordinary journey through theoretical physics to explore this groundbreaking idea. Buckle up as we delve into the 13-dimensional universe, unraveling the theories, implications, and the very nature of these elusive dimensions. Theoretical foundations. String theory and beyond. String theory, a prominent framework in theoretical physics, posits that fundamental particles are not point-like dots, but rather one-dimensional strings vibrating at different frequencies. This theory requires additional spatial dimensions for mathematical consistency, originally proposing 10 dimensions plus 1 time dimension, which later evolved into the more comprehensive M theory, suggesting 11 dimensions. These additional dimensions are necessary to unify the 4 fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single coherent framework. By introducing extra dimensions, string theory provides the mathematical tools needed to describe these interactions in a unified manner, potentially solving one of the most significant challenges in modern physics. M theory. M theory unifies the 5 different string theories and introduces the concept of membranes or branes that can exist in higher dimensions. This theory requires 11 dimensions, 10 spatial and 1 temporal. The discovery of the 13-dimensional model stems from attempts to reconcile inconsistencies within M theory and quantum gravity. M theory's inclusion of branes adds a new layer of complexity, suggesting that our universe might be a 3-dimensional brane floating in a higher dimensional space. This perspective opens up possibilities for understanding phenomena like black holes and the Big Bang in new ways, as these higher dimensions could influence events in our observable universe. Describing the 13 dimensions, the observable dimensions. The first dimension is the simplest, representing a straight line with only 1 coordinate length. In this dimension, objects can move forward or backward along a single axis. This one-dimensional space is foundational in geometry and serves as the basis for more complex spatial constructs. For example, consider a line drawn on a piece of paper. It has only 1 dimension, length, and no width or depth. Understanding this basic dimension is crucial as it underpins the concept of spatial extension, allowing us to build more complex structures from this simple foundation. In physics, the first dimension provides the baseline for defining position and distance, crucial for describing the simplest forms of motion and structure. Adding a second coordinate creates a plane with length and width. This dimension allows for the creation of 2-dimensional shapes, such as squares and circles, and introduces the concept of area. Objects in this dimension can move in 2 perpendicular directions, enhancing the complexity of spatial relationships. A classic example is a sheet of paper, which has both length and width but no appreciable depth. In mathematics and physics, the second dimension is crucial for describing surfaces and interfaces, which are essential in fields ranging from cartography to material science. This dimension is also pivotal in graphing data and understanding phenomena that can be represented on a plane, such as wave patterns and heat distribution. Introducing the third coordinate forms a 3D space with length, width, and depth. This is the familiar 3-dimensional space we experience daily, where objects have volume and can move in 3 independent directions. This dimension is crucial for understanding the physical world, as it encompasses the spatial attributes of all matter. For instance, a cube has dimensions of length, width, and depth, making it a fully 3-dimensional object. In everyday life, this is the dimension that allows us to perceive the volume and shape of objects, making it fundamental to our interaction with the physical world. In science and engineering, the third dimension is essential for understanding forces, structures, and physical interactions that define the material world. Incorporating time as the fourth dimension is essential for describing the position of objects in the space-time continuum. Time allows us to track the sequence of events and the evolution of systems. In the framework of Einstein's theory of relativity, time is intertwined with the 3 spatial dimensions to form space-time. where the fabric of the universe is shaped by mass and energy. This dimension is crucial for understanding dynamics and changes over time. For example, in physics, the position and velocity of a moving object can only be fully described when time is included as a parameter, highlighting its importance in our understanding of the universe. Time's integration with space forms the basis for modern physics' understanding of how objects move and interact on both large, cosmological, and small, quantum, scales. This dimension introduces the concept of alternate realities or parallel universes, where different outcomes of events occur. Each possible world represents a different version of reality, determined by varying initial conditions and choices. This idea is foundational in the multiverse hypothesis, where every possible scenario exists simultaneously in a vast landscape of potential universes. In this dimension, the concept of what if becomes a reality, allowing for the existence of countless alternate histories and futures based on different decisions and events. This dimension expands our understanding of reality, suggesting that every possible outcome of every event creates a new universe. This concept is crucial for theories that attempt to explain quantum mechanics' probabilistic nature and how multiple possibilities can coexist. In the sixth dimension, known as folding possible worlds, we encounter a realm that enables movement between different possible worlds, allowing for the exploration of alternate realities without restrictions. This dimension adds a new layer of interaction, where transitions between these worlds are possible. It suggests that pathways or connections exist between different realities, potentially enabling travel or communication across parallel universes. This concept is often explored in science fiction, where characters can move between different versions of reality, but it also has serious implications for theoretical physics and the nature of reality itself. The ability to traverse different worlds could provide insights into the fundamental nature of space and time, and how different universes might influence each other. This dimension could explain phenomena like quantum entanglement, where particles seem to instantaneously affect each other across vast distances. The seventh dimension, known as all possible worlds with different initial conditions, expands the sixth dimension by considering worlds that start with different initial conditions, but are governed by the same physical laws. This dimension includes all variations of the universe that could arise from different starting points, encompassing a broader spectrum of possibilities within the same fundamental framework of physical laws. It highlights the importance of initial conditions in determining the evolution of a universe and suggests a deeper underlying order governed by consistent physical principles. This dimension allows for the exploration of how slight differences at the beginning of a universe can lead to vastly different outcomes, illustrating the sensitivity of physical systems to initial conditions. It is akin to exploring a vast branching tree where each branch represents a different potential universe that evolves according to the same fundamental laws but from different starting points. Beyond the seventh, the eighth dimension encompasses universes where fundamental physical laws differ. These differences could be in the nature of forces, constants, or even the structure of space-time itself. The eighth dimension represents a more radical departure from our own universe, where entirely new forms of physics could exist. It suggests that the physical laws we observe are not unique, but are one set among many possible configurations, each giving rise to a different kind of universe with its own unique properties and behaviors. This dimension challenges the assumption that our physical laws are universal, proposing instead a multiverse where each universe operates under its own set of rules. This concept is essential for understanding the ultimate diversity of possible realities and how our universe fits into a broader spectrum of existence. In the ninth dimension, we explore the comparison of all possible laws of physics. This dimension allows for the comparison and interaction between different sets of physical laws across infinite universes. It facilitates the study of how different physical laws can coexist and influence each other, providing a meta-framework for understanding the diversity of possible universes. Moreover, it opens up the possibility of discovering universal principles that apply across all realities. This dimension could be key to developing a truly unified theory of physics, capable of describing all possible forms of existence. By comparing different sets of physical laws, scientists can seek overarching principles that govern the multiverse, potentially leading to breakthroughs in our understanding of fundamental physics and the nature of reality itself. The 10th dimension involves folding all possible laws of physics. It facilitates transitions between universes with varying physical laws, akin to the 6th dimension but on a larger scale. This dimension suggests that connections or pathways exist between fundamentally different universes, allowing for the exchange of information or even matter between them. It proposes a higher-order structure where the multiverse can be navigated despite the diversity of physical laws. This concept challenges our understanding of the barriers between different realities and suggests that there might be ways to bridge these gaps, opening up new possibilities for exploration and interaction. The idea of folding different physical laws into a navigable framework implies a more interconnected and dynamic multiverse than previously imagined, where different universes might influence each other in complex and profound ways. In the 11th dimension, we delve into membrane theory, part of M-theory's additional dimension. This dimension incorporates branes, multi-dimensional objects that can exist within the higher dimensional space. Branes can be of various dimensions and interact in complex ways, potentially explaining phenomena like the Big Bang as collisions or interactions between branes. This dimension also introduces the idea that our universe could be a brane within a higher dimensional space, influencing and being influenced by other branes. This perspective offers a new way to think about the origin and structure of our universe, suggesting that many of the most fundamental events in cosmic history could be the result of interactions in higher dimensions. Such interactions might manifest as gravitational waves or other detectable effects that could provide evidence for the existence of these higher dimensions. Twelfth dimension, compactified dimensions. These dimensions are theorized to be compactified or curled up at every point in our universe, influencing particle interactions and forces at microscopic levels. Compactification explains why higher dimensions are not directly observable, as they are extremely small and tightly wrapped. These dimensions can have profound effects on particle physics and the fundamental forces, potentially offering insights into the nature of gravity and other interactions. For instance, the properties of elementary particles and the strengths of fundamental forces might be determined by the shapes and sizes of these compactified dimensions. Experiments at high-energy particle colliders, such as the Large Hadron Collider, seek to uncover indirect evidence of these compactified dimensions by detecting deviations from the standard model of particle physics. Thirteenth dimension, the landscape of universes. This final dimension suggests a landscape of all possible universes, each defined by different vacuum states in string theory, allowing for a multiverse of realities. The 13th dimension encompasses the idea that each universe in the multiverse is a point in a vast landscape, determined by different configurations of compactified dimensions and physical laws. This concept offers a comprehensive view of the multiverse where every possible variation of reality is represented. It suggests that our universe is just one of countless possibilities, each with its own unique properties and laws, existing within a grander framework of reality. This dimension implies a higher-order level of structure to the multiverse, governed by the principles of string theory and the configurations of its fundamental components. Implications of the 13-dimensional universe. Unifying physical theories. The primary goal of introducing additional dimensions is to reconcile general relativity, which describes gravity at large scales, with quantum mechanics governing subatomic particles. The 13-dimensional model provides a robust framework for this unification, offering potential solutions to previously unsolved problems in both fields. By incorporating higher dimensions, physicists can develop theories that encompass all fundamental forces and particles, leading to a more complete understanding of the universe's underlying structure. This unification is often referred to as the theory of everything, aiming to describe all physical phenomena within a single, coherent theoretical framework. The additional dimensions provide the necessary degrees of freedom to solve inconsistencies between the two theories, such as the behavior of gravity at quantum scales. Experimental evidence and challenges. Detecting these extra dimensions directly poses significant challenges due to their compactified nature. However, scientists are exploring indirect methods such as studying the cosmic microwave background, particle collisions at high energies, and gravitational waves for signatures of higher dimensional phenomena. Experiments at facilities like the Large Hadron Collider aim to uncover evidence of extra dimensions by observing deviations from expected particle behaviors. Additionally, advanced telescopes and observatories are searching for subtle anomalies in cosmic radiation that could hint at the influence of higher dimensions. These efforts are at the forefront of experimental physics, pushing the boundaries of our detection capabilities and potentially revealing the hidden structure of our universe. The proposal of a 13-dimensional universe is a bold and revolutionary step in theoretical physics, pushing the boundaries of our understanding of reality. By exploring each dimension in detail, this paper has highlighted the profound implications for unifying physical theories, understanding dark matter and energy, and expanding the concept of a multiverse. As research progresses, the mysteries of these higher dimensions may eventually unfold, offering deeper insights into the fabric of the cosmos. The 13-dimensional model provides a comprehensive framework for addressing some of the most fundamental questions in physics, potentially leading to breakthroughs that could transform our understanding of the universe and our place within it. While direct evidence for these dimensions remains elusive, the theoretical advancements they offer are compelling, suggesting that the true nature of reality may be far more complex and wondrous than we currently comprehend. Thank you for joining us on this incredible journey through the 13-dimensional universe. This was just another file opened beyond our imagination. If you enjoyed the video, please like so we can get this video to as much people as possible out there. Subscribe, hit that bell notification for alerts on all our new videos, share and comment below on topics you want us to cover on the channel. Thanks for watching and see you on the next one.